Okay, yeah, you're good to go. Okay.
Good morning to professors and colleagues in Singapore, and good evening to professors in US. Thanks to people at both the sides for making up to attend my presentation. So my name is Sharad, and I'm a PhD candidate in School of Computer Engineering at NTU in Singapore. I'll be giving a talk on complex electronic systems from hardware to system resiliency. And the talk is divided into two parts. So the first part, I'll deal with my PhD work. I'll give a brief introduction to that. And the second part, I'll talk about system resiliency and security specifically for critical infrastructure systems, especially targeting the smart grid applications. Now, before I give my talk, I'd just like to share with you people my experience so that you know where I'm coming from. So I worked in the industry for 2 years, and I designed FPGA-based embedded systems. And as part of that, I worked on communication protocol implementation, cryptography-related work, as well as digital image processing-related work. I also did fault tree analysis and failure mode effects and criticality analysis for defense systems. And as part of those projects, I also had the chance to look at safety-critical software design practices, as well as military specs and standards. Thereafter, I started my PhD, and as part of my PhD, my main focus was to address design complexity and time to market pressure through improved high-level synthesis methodology. And during my PhD work, the main ideas that I focused on was to generate and exploit application awareness, and exploit the target architecture awareness, and exploit system-level constraints. I am also associated with 2 startups in Singapore in advisory capacity. One is called Ideatory, which works on crowdsourced innovation for embedded system projects, which it gets from small and medium enterprises here. And the other one is Nucleus Dynamics, which works on cloud-based chronic wound management through image processing and 3D modeling. Okay, so this is the overview of my presentation. So the first half, I'll talk about electronic system level design, basically about design and verification complexity, which is a cause for concern, and how has the community tried to address these complexities. High-level synthesis being one of the methodologies, so I'll deal in brief about its past, present, and future, as well as include my contributions in this space. The second half of this talk will talk about system security, so I'll present ideas, some of which I've been working on, and ideas about research in this space in general, at the device level, at the network level, and at the system level. Okay. So these two graphs you guys might be familiar with. So the graph on the left basically shows the productivity gap in electronic system design. So the blue curve shows the number of transistors that's increasing on a chip, and the red curve shows the productivity of engineers. And if you can see the green box there, that shows that there is a gap in between these two. Similarly, the graph on the right shows the complexities of features that are being implemented on these systems, both in hardware and software, and how is this faring up with the efforts of designers. So there's a gap there also. But apart from these two gaps, we should also not forget that there's a shortening time to market, especially for certain industries like consumer electronics, and there's an increasing non-recurring engineering cost associated with products that make use of ASICs and similar platforms.
So your red curve is more for the software design or the
Okay, the curve on the right is for the hardware design, and the graph on the left is for hardware design, and the graph on the right is for both hardware and software.
Okay.
So how has the community tried to address these two concerns? So in the hardware space, people have come up with model-based hardware design that includes your Simulink plus HDL coder, Xilinx system generator, Aldera DSP builder, and similar methodologies. There's also IP core based hardware design, where you collect and assemble pre-verified RTL blocks and you make your system that way. And there's another method, which is high-level synthesis, which basically looks at abstracting the complexities at the RTL level so that you express your design in C, C++, or System C, and from there on you move to generating your architecture. In the software front,
So Sharad, I have a, I can ask a question. Where does in this, companies like Tensilica and which now of course belongs to Cadence, where do they fit in?
okay, Tensilica fits somewhere in the space of IP core based hardware design and a little bit of high level synthesis, though their methodologies is different and they are more focused on processor design. So you can customize the processor from using a high level description of the processor, and that is how they generate, and you can get an RTL and then you can fabricate the chip for you. So if you are looking at customized processor design, you don't have to do everything at the RTL level. You can describe your processor using their processor description language, and then using their tool flow you can generate the RTL, and then you can give that RTL to your foundry and the foundry will fabricate for you.
Yeah, please go ahead.
Yeah. In the software space, people have worked on model-based software design. So you have the Unified Modeling Language (UML), which is one of the ways to model the different kinds of software which are being designed. If you are doing software for system-on-chip design, you have a specific UML profile for that. And if you are looking at code, software code at the embedded level for microprocessors and microcontrollers, you have the Simulink plus embedded coder flow. At the same time, you also have software reuse based concept in software design, which basically looks at reusing pre-verified software modules like libraries and packages and things like that, so that you don't have to do that stuff again and again. And there's another one which is not so common, but it's slowly evolving, is the design patterns based software design, where you look at the common patterns of computation that are there in applications, and then you implement them in generic ways so that you can use them in different applications. Okay, now, so I'll talk about high-level synthesis, as I said, because this is the space in which I have done my most of my PhD work. So high-level synthesis for chip design has been an active area of research for more than 20 years, and most of that research has focused on area reduction, basically reducing the resource utilization, scheduling, as well as supporting C and C-based language and their constructs to generate RTL. So what is the present? At present, you have commercial tools like Vivado HLS, which is from Xilinx. You have Catapult C, which is from Electro Design Systems. Similarly, you have tools from Synopsys and Cadence. But the tools have limited adoption and it's slowly increasing. But it's nowhere near to your traditional RTL-based design methodologies. So what does high-level synthesis basically have? So high-level synthesis, this is a typical flow of high-level synthesis. So you begin with a specification of your design, of your algorithm, which would be in C or C++ or System C, because these are the three commonly supported and agreed upon languages in the community, though there are other languages also which people have worked upon. So you take that specification, you compile that, as a result of which you get a formal model of your application. So this formal model is basically the control and data flow graph of your application. Once you have that in place and you have a library of components for your target technology, if you're doing it for ASICs, or if your target device, if you're doing it for FPGAs, thereafter you allocate those resources from the library and you schedule the operations that are there in the control and data flow graph based on data dependency and other scheduling constraints. And thereafter, those operations in the control and data flow graph are bound to the resources that have been allocated. And these resources could be your functional units, as well as multiplexers, buses, memory elements, etc. At the end of which, the RTL microarchitecture is automatically generated, and thereafter, it's your normal physical synthesis flow. So where is the challenge in this space? Hardware design has traditionally been a person-dominated area. So you have an expert who does the design for you. So you have a chip designed by an expert, and high-level synthesis is more like an automated methodology where a computer or an algorithm does it for you. So you begin with a description and the tool does everything for you, or the flow is supposed to do everything for you. So these two So these two flows will give you a design. So what is the quality of result between these two designs? That is the challenge. How do the two match up against each other? Just a brief detour on what is quality of result. So traditionally, the quality of result has been associated with resource utilization, time performance and power consumption. But if you look at hardware design, there's also concerns about verifiability as well as design for test. So these two, the two points at the last, verifiability and design for test, are some of the upcoming challenges in high-level synthesis. Okay, I'll now just talk briefly about my PhD contributions. I'll tell you a story, and the story basically connects the different pieces of my PhD. That story is more like a flow. So this flow isn't validated from top to bottom, but its individual parts have been validated, which I have worked upon. So you begin with a scheduled and word length optimized application data flow graph. Now this part has been done by compilers and others, which is not part of my work, and you have an IP core and target device library. Thereafter, you analyze the data flow graph for C or C++ inbuilt functions, like sine, cos, and others. You also analyze the data flow graph for the IP core patterns. So you look for those patterns for analysis and matching. On the extreme right, the red vertical line, if that represents your C code, so at the end of this step, you are able to identify which are the code segments in your application which are candidates for mapping to IP cores. Thereafter, we look at the DFG analysis for multiplication operations specifically, because multiplication is a costly operation in hardware, and we analyze the application for different kinds of multiplication operations, and then we look at mapping of those operations to the available on-chip DSP blocks. So at the end of this step, you are able to identify in your application which are the operations which can be mapped to the DSP blocks. After this step, you have your annotated data flow graph, and in some applications, you can also have a data initiation interval constraint, which is represented here as the interval constraint, which basically says that how often are you going to feed a new set of input data to your application. So we use that information to partition the data flow graph into different partitions, and then later on we stitch those partitions in time. Now why we do that partitioning is because after this step, we want to share the resources within that partition. Now at the end of this step, if you have any more resources left or freed because of sharing, you can use those resources again to map certain other operations that were left earlier to the DSP blocks. And finally, you have the RTL data path. And then from there onwards, you have your normal physical synthesis. So I'll give examples of what I mean by application architecture awareness. So this is the first example. So the aim here is to automatically identify different functions in an application and map them to FPGA specific IP cores. Now, by functions, I don't mean the user-defined functions. By functions, I mean the keywords as well as the patterns, the graph patterns of different computational structures. So we proposed some algorithms here to automatically identify, select a suitable IP core, and then do an interface synthesis. An example result is here where you have the greater circle distance formula, which is part of GPS calculations that has been implemented. So the tall blue bar graph is basically the implementation results that you get using a commercial tool, which is Vivado HLS in this case, and the three shorter bar graphs are the results that you get if you use if you follow the methodology that has been proposed. And if you can see here, the tool can give you one design point for a given clock period constraint, but if you follow the methodology that has been proposed, you can get more design points, all of which satisfy the same design constraint. Now the other example is you have large applications like like a matrix multiplication where you have two very large matrices and or very large FIR filters. So how do you map those large number of multiplication operations to the limited DSP blocks on an FPGA? So we proposed a certain methodologies looking at automatic identification of those operations first, because typically a hardware designer would do it manually. He would be able to look at the application and identify, but how do you do it automatically? So this one was that step, and then we did some cost estimation, some cost model, and finally mapping. So here are two examples of the results. So you have a 53 tap FIR filter, and if when it was implemented using Vivado HLS, a commercial tool, the timing constraint at which it could give you a working design was 20 nanoseconds, whereas with our flow we could hit a speed of a clock period of 6.9 nanoseconds, so which is significantly faster. Similarly for the 40 by 40 matrix multiplication as well.
Sharad, what was the issue with identifying the authentication and the operations that you identified?
Okay.
You said you automated.
Yeah. So
How was it sort of?
okay, so in an application you can have single constant multiplication. You can have different kinds of multiplication operations. So you have the single constant multiplication, you have the multiple constant multiplication, and you have the variable being multiplied by variable. The existing HLS methodologies treat all kinds of multiplication as equivalent, as a result of which you are not able to exploit the specific ways of implementing these different kinds of multiplications in hardware. From a software perspective, this might all look same, but from a hardware perspective, there are different ways of implementing each of these in hardware. So normally, a hardware designer will do it manually. So he'll be able to look at the initial hardware architecture document and see which are the kinds of multiplications and choose where to map which. But in an automated flow, where you begin from a software-based description, you cannot do it automatically, or even if you're able to do it automatically for very large applications, it won't be possible. So that was the reason why we decided to look at automating this step.
So what's the impact on applications of these results? Let's say if you can do the 40 by 40 matrix, it's not a big scale matrix multiplication, right? But I assume it's some building block that's used by, so what would be the end user benefit of playing?
The end user benefit of looking at the proposed flow is that you can have a design which works faster. Because if you can identify these operations automatically, and you know where these kind of operations can be mapped to resources on the target device.
But it would translate to, for example, what kind of application improvement? So I understand you can do it faster, okay?
Yeah.
Faster at this level, right? So if you scale it up to, the end application, what is the impact?
So if you scale it up in end applications, in an end application you can have different other operations. Now when you're doing it on hardware, the critical path will be dictated by the kind of operations that use a lot of resources. And multiplication being one of them, so if your application is dominated by multiplication operations, and if you just implement them in your normal FPGA fabric and don't utilize the DSP resources, you are going to have an application which runs very slow. So
at the end of the day, what kind of improvements do I get?
If you take any real application.
Yeah, take a real application.
Okay, I have not taken a real application for this particular case, because the point here was to demonstrate that this thing can give improvement. But real applications like in computer graphics, you have the 3D modeling of structures, and then you do translation, rotation, and other effects on them. So that can be speeded up. So normally, if you do that you can do that in different other ways, but this is one of these.
So how did you measure the speed up then? You said you did it in
Okay.
6.9 nanoseconds.
Yeah.
And you used so what was it? What was the application? Oh, this is the tap FIR filter.
So this the 6.9.
So that was your.
Okay.
Sorry, go on.
Yeah. So this 6.9 nanoseconds here shows the the fastest rate at which you can drive your clock in your hardware design. For the commercial tool, the fastest that your clock can go is with a clock period of 20 nanoseconds, which is I guess 50 megahertz. Whereas with the proposed flow, it's 7 nanoseconds. It's around 7 nanoseconds, so that's around 120 megahertz. So you can have a faster clock